Hello viewers, welcome back to your own chemistry channel and you're watching DMG chemistry classes and myself Dr. Mahendra Guleria, Associate Professor in Chemistry. And in this video I'm going to talk about the law of chemical equilibrium and I will also discuss the different types of equilibrium constants. So please keep watching this video till very end and also subscribe my channel. So friends, before coming on to this topic, I would like to give you an idea about the law of mass action. And according to this law, the rate of a chemical reaction is directly proportional to the product of molar concentrations of reactants with each concentration term raised to the power their respective stoichiometric coefficients. And by stoichiometric coefficients we mean the number of times that reactant appear in the balanced chemical equation. Okay, and the molar concentration is also called as active mass. And what is molar concentration? It is the number of moles dissolved per liter of the solution. And I will explain this law during this video. Okay, so friends, when this law, that is law of mass action, is applied to a reversible equilibrium reaction, then the result obtained is called as law of chemical equilibrium. Okay, so now let us discuss this law in detail and deduce its mathematical expression. And to derive it, let us consider a general reversible reaction in which A moles of A are reacting with B moles of B, giving us L moles of L and M moles of M. And these A, B, L, M are also called as the stoichiometric coefficients of A, B, L and M respectively. Understood? And as I said, according to the law of mass action, the rate of forward reaction Rf will be directly proportional to the product of molar concentration of the reactants. Okay, so here the A written inside the square brackets represents the molar concentration of A, and B written inside the square brackets represents the molar concentration of B. Okay, and each concentration term is raised to the power their respective stoichiometric coefficients, that is A raised to power A and B raised to power B. Okay, and I have told you that when this proportionality is converted into an equality, then we always have a constant. Then this equation will become Rf is equal to Kf into A raised to power A and B raised to power B, and this is equation number 2. Okay, and this Kf is a proportionality constant and it is called as the rate constant for the forward reaction. Okay, so likewise, according to the law of mass action, the rate of backward reaction Rb will be directly proportional to the L raised to power small l and this capital M raised to power small m. And likewise, Rb will be equal to Kb into L raised to power L and M raised to power M, where Kb is the rate constant for the backward reaction and it is also a proportionality constant. And I have told you in my previous video that at equilibrium, rate of forward reaction is equal to the rate of backward reaction. This means that Rf is equal to Rb, then left hand sides are equal, then their right hand sides will also be equal. This means that Kf into A raised to power A and B raised to power B will be equal to Kb into L raised to power L and M raised to power M. Okay, and when we will rearrange this equation, we will have Kf upon Kb equal to L raised to power L into M raised to power M divided by A raised to power A and B raised to power B. And as I said, both Kf and Kb both are constants, okay, at constant temperature. So their ratio will be another constant at constant temperature, and that new constant is written capital K here, and capital K, it is equal to Kf upon Kb and it is equal to this quantity. Okay, so this K is called as equilibrium constant and this expression number 4 is called as law of chemical equilibrium. So now let us define this law of chemical equilibrium. According to this law, the ratio of the product of molar concentrations of products to the product of molar concentration of the reactants with each concentration term raised to the power their respective stoichiometric coefficient is constant, and that constant is called as equilibrium constant at constant temperature. So let us write the statement of this law. Okay, that is the ratio of product of molar concentrations of products to the product of molar concentrations of reactants with each concentration term raised to the power their respective stoichiometric coefficients is constant at constant temperature. At constant temperature, and that constant is called as equilibrium constant. Okay, so this is the law of chemical equilibrium. Now let us discuss the different types of equilibrium constants. That is types of equilibrium constants. Okay. So friends, when the molar concentrations are used in the expression for the law of chemical equilibrium, then the equilibrium constant is called as equilibrium constant in terms of concentration. Okay, and it is represented by Kc. So here this K, because here we have used what? Molar concentrations. Then this K will be called as the equilibrium constant in terms of molar concentrations, and it will be represented by Kc. So the Kc will be equal to this, that is L raised to power L into M raised to power M divided by A raised to power A and B raised to power B. Okay, and sometime the molar concentrations are also represented like this, that then the Kc will be equal to, that is Cl raised to power L into Cm raised to power M and Ca raised to power A into Cb raised to power B. So these two expressions are for the Kc. Okay, and when all the reactants and the products are gases, okay, that is all the reactants and products are present in the gaseous phase, then we will use the partial pressures of the reactants and the products, and the equilibrium constant will be called as the equilibrium constant in terms of partial pressures, and it will be represented by Kp. Then Kp will be equal to Pl raised to power L into Pm raised to power M divided by Pa raised to power A and Pb raised to power B. Okay, so this is the expression for Kp. Understood? And if mole fractions are used, then the equilibrium constant will be represented by Kx, and it will be equal to Xl raised to power L Xm raised to power M divided by Xa raised to power A and Xb raised to power B. Okay, but it is more appropriate to use activity. Okay, activity in place of this partial pressure and the molar concentration, and I will discuss or I will explain this term activities in my upcoming videos. Okay, and if activities are used, then we will have the equilibrium constant in terms of activity, and it will be represented by Ka. Okay, and then Ka will be equal to, that is activity of Al raised to power small l, likewise Am raised to power M divided by Aa raised to power A into Ab raised to power V. So this is the equilibrium constant in terms of activities. Okay, so these are the different types of equilibrium constants, and in my next video I will derive very useful and very important relationships between these different types of equilibrium constants. So keep watching my videos, like and share my videos, and subscribe my channel. Thank you very much.